Okay, so we've talked a little bit about what vector is versus a scalar. How you work with vectors is all the same, doesn't matter what kind of vector it is. However, how you draw the vector and how you label the vector can be different. It depends on what you're talking about. We're talking about position, displacement. We'll talk about that here in a second. It's not too hard, but get this straight, and the notation shouldn't get in the way. So recall that we had four representations of vectors. So when we're talking about a vector, we want to have vector variables. We can write a bold letter, if you can write a bold letter, or type it. Or often we'll do the letter with a little half arrow or full arrow, either way, on top. It says direction matters. Arrows are drawn with a tail and a tip in a particular direction. Polar form is the amount with units and the direction. Component form is the amount in each direction, the amount in the x direction with units. And you can put a comma in between amount in y direction with units. But that's a little bit clunky. It works out better just to say the amount in x direction with units times I hat, which only means in the x direction. It means you can't add these numbers. This is 5 meters, that's 2 meters. You can't add that to 7. This is just sort of like the comma. Keep it separate. And we'll see how you work with that later. So the amount in the x direction with the unit I hat plus the amount in the y direction j hat. If you've got z, the amount in the z direction times k hat. That's just our bookkeeping that keeps the columns, keep those numbers separate. Okay, but don't forget the units because you'll forget what it means, and also the number doesn't mean anything without the units. So it seems to be a lot to write, but the more you write, the faster you get, the better. Right now I want to look at 5 vectors in particular to get us started. The position vector, the displacement vector, the velocity vector, the acceleration vector. So those are kinematics. Acceleration describes the rate at which velocity changes. Force is going to be the cause of the change in velocity. Okay, acceleration doesn't cause change, it just describes it. So let's see how we notate that. All right. So position, and of course we're only doing 2D for starters. So position, we've got some coordinates, x and y, we'll talk about that next time. Maybe position 1, position 2, position 3, I'm not sure what the path is, I can get there in many ways, right? Okay, so how do I draw a position vector? Well, the tail is at the origin, wherever you choose. So here's an axis, I could choose the origin right here, I could choose the origin wherever I want, I could choose positive the other way. So once you set that up, fine. The position, the tail is at the origin, the tip is at the position. All right, so let's do that for 1. That would be the tail at the origin, the tip here. And that length represents how far away you are from the origin. Now, how do I write the notation for that as a variable? Well, we use r. You can kind of see why. Here I would say r1. And then where would position 2 be? Well, it would be up there. It would be R2. And then position 3 would be radially out, hence the R, from the origin straight out there. So that's why we usually use R as our vector variable. But you can see that if I were at 1, I would be some amount in the x direction and some amount in the y direction. And so how we're going to deal with vectors is to divide and conquer. Divide up the x parts and the y parts. Okay? So in polar form, we've got R2. And this is a good point. You could either write the amount as R2 without the arrow. Now, you'll be unusual if you catch on this early, but try it. If you put the arrow in, you're saying, I'm including the direction. If you're leaving the arrow off, I'm saying just the amount. Okay? Or you could put absolute value signs around there, and sometimes you'll see double lines. You can worry about that later. Around R2. So this is saying the amount, and this is saying the amount. What direction? Well, the direction is given by some convenient angle. It's whatever direction that is. So for example, if I want to talk about the direction of R1 here, I could use this angle, or I could use this angle. It doesn't matter. If I describe it correctly, it's still the same position. Okay, so we'll work with that a little bit later. So that's how you talk about the polar form. How far away from the origin and in what direction. Or component form. position 1 or position 2 in this case. Here's position 2, so I was talking about, I've written down position 2 here, so that I could give the angle up from the x-axis, down from the y-axis, whatever it is. Position 2 has some x component and some y component. So you can write the variable R2. Notice that I do not have the hat on top, or the arrow, the half arrow. I just have the amount, and this says in the x direction. The amount, and this says in the y direction, but I have subscripted at x and y. Since it's position, we know that the position variable is usually just written as x instead of rx. X at 2, position 2, and the y component at position 2. x2 I hat plus x2 j, or excuse me, y2 j hat. You could just as well write this like that, but it's not as easy to work with. And so those unit vectors, so-called, should be called direction vectors. Those direction vectors really are kind of nice to say. I'm talking, I got that much, that direction, I got that much in that direction. Okay? So you can see each of these positions has an x amount and a y amount, an x amount and a y amount, which are plus or minus. Now, position can vary with time. So maybe position is given as a function of time. Then x changes with time, so there's some function here. So that's x changing with time in the x direction. Y, a function changing with time in the y direction. Z is a function of time times k hat if you were to go there. And that's how we write it. That's all there is to that one. Okay, let's try displacement, then we'll work with it. And as you work with it, this will all kind of settle in. So displacement. Where do we draw the arrow? It's a little different. The tail is at the earlier position, and the tip is at a later position. So notice displacement happens between two states. Position is at a state, a moment, an instant. Okay. So at an early position and the tip at the later position. The variable, you can write D, capital D I like, with an arrow on top. You'll see that sometimes. From earlier to later, 1 to 2, 1 to 3, 2 to 3, whatever. Or you can write it as delta R, because it is the change in position vector. Okay. So let's do that. Let's see, this is position 1, position 2, position 3. Notice that if I do the position vector, I'm going to go here. Boom. That's a position vector. Position vector 2 will be here. My displacement, or change in position, would be from, let's do it this way, 1 to 2. Now this occurs in time. So it was at position 1, and then it was at position 2. I can't go 2 to 1, that's going backwards in time. I don't know how I got there, and it doesn't really matter what the path was. The displacement is from earlier to later. Okay? That is the change in your position vector, which we'll deal with later, from 1 to 2. Now if I want from 1 to 3, then I go straight from 1 to 3, independent of the path. If I want from 2 to 3, well, of course, that would be my delta R, or my displacement from 2 to 3. And that's how you draw that. Okay? It's got a certain amount, and it's got a certain direction, straight from the earlier to the later. You can draw it as this, you can just draw it as D without the arrow, or whatever however you want to use, whatever notation. In component form, well, when you change position, you change some in the x, and you change some in the y. Here I did it from 1 to 3. So if I'm changing position from position 1 to 3, no matter what the path is, you go straight from 1 to 3. That's my displacement, independent of the path. That is my displacement from 1 to 3. Okay? And I can write that as a, notice that there would be a change, and this is going to be critical. there's the change in x, right? And I like to put that as a dash. You'll see that later. There's my delta x from 1 to 3. Negative, isn't it? And here's my delta y from 1 to 3. And if I were to go this way, I'd end up in the same place. Okay, and that's how I write that notation. Meters, meters, centimeters, nanometers, whatever you have. Miles. That's velocity, how do I do that? Okay, well, velocity, remember the arrow. We've done this in 1D, now we're going to 2D, leaving 3D for later. The tail is usually drawn at the object. The tip directs, it's in the direction you're going at that moment. Now if you're turning, maybe, at 1, you're going to 2, but how you're getting there, think of it as the direction you would go if you hit ice and you just kept sliding. So if my path happened to be that, then at state 1, I would draw my velocity, usually right here, and just kind of draw a tangent. How long? I don't know. V1. Now I like to show the direction with my arrow and put the amount, which would be the speed, next to it. Some people put the arrow on top. There's a reason when we get into force analysis why I think that leads to confusion. Either way can work as long as you're clear. So that's the direction. And 2, well, I have to know which way I'm going. If I went like this, if this kept going like this, and I went like that, then 2 is going to be tangent if I'm going that way. 2 is going to have a velocity v2 here, and 3 is going to have a velocity v3 here. Okay, tangent to the path, that's all. And the variable would be v1, v2. And that arrow says, hold on, you can't just add up velocities, you've got to account for the direction. We've got to use a little trigonometry here. So polar form, I would say v1, for example, would be the magnitude of v1, or simply v1 without an arrow. If you write that, you're not taking into account the direction without the arrow. This takes into account the direction. And it says it's got a speed and a direction tangent to the path, which can be given by an angle. We'll see the specifics of that as you're working through. Of course, at any moment, I've got a velocity, which means I've got a direction and a speed. But if I think about it, that means that I'm moving partly in whatever direction I called x, and partly in whatever direction I called y. So there's the x component at that moment, and the y component at that moment. So we can write that v at that moment 1, x part, and y part. So each of those vectors has a component moving that way in the x and moving that way in the y. So we'll see that. You could also write it as dx dt evaluated at time 1 and dy dt evaluated at time 1 for v1. Okay, so there's that. It's similar, right? But each vector means a little something different. So acceleration, I won't draw this, I'm going to do this kind of quickly. We've talked about this some, but you just usually place it next to the object. So we know that if you're increasing speed, then you draw the acceleration vector parallel to the velocity. If you're decreasing, then it's opposite or anti-parallel, or parallel to negative v. If you're turning at a constant speed, then it's perpendicular and directed into the turn. Or you could have a combination where you're changing speed and changing direction. So, vector A, some amount, the direction. It's got an x component and a y component with my coordinates. What does that mean? Sometimes you just, that's all you need. Sometimes you'll write it as dvx dt, the rate of change of velocity in the y direction, dt, j hat. Don't get overwhelmed. But sometimes we'll actually write this as a vector part for changing speed and a vector part for changing direction. So you'll see with examples, and you have to play with that. Okay, so one more that I promised. Let's take a look here. And let's go to the mid part here. Component form, polar form, variable, tail at. And what I want to do is force. Force is a push or pull. We're going to learn about that soon. So force, and you cannot push or pull in no direction. Okay? The magnitude of velocity is the speed. The magnitude of position is how far from the origin. The magnitude of displacement is how far away you ended up from your earlier state. But what is force? Force is a push or pull. So you draw an arrow, tail at the object, usually, often. The tip directed in the direction of the force of your push or your pull. I'll show you in a second. The variable, what do you think? How about F? And there's going to be lots of variables. We'll get into different. There's the force of tension. We sometimes put that. The force of gravity, sometimes G or uppercase G. There's the electric force. There's the magnetic force. So we often subscript that, however we do, and we can write the force of friction and so on. Lots of forces. We'll get into that later. But the polar form is simply like that. So the point is that it's F is equal to the strength. So the magnitude of force is the strength. You can just write it that way. And then again, you've got to give some angle for the direction. And you could write that F, or you can write that F like that. That's the how much. Component form is this. Well, I don't know, I've got some push in the x direction, and some push in the y direction. But if I wrote that, that would be crazy because I could add these two up. I need to say I can't add them. This is in one direction, and this is the amount in another direction. So for example, if I've got an object here, and I'm sliding along the table, and I'm pulling on a rope, and there's a force this way of tension, well, you might want to, for whatever reasons, for analysis, say I'm pulling it horizontally this much, and I'm pulling it up this much. This might be my force X, and this might be my force Y, and so on. But it's still the same idea. You've got an amount and a direction, but the meaning is very different. And so that gives you, hopefully, some idea of the notation that would be used, and then we'll do some examples.